Hello, here we will apply the diagonalization for computing function on the matrix. And the matrix will be this easy one. And the function will be just 2 to the x. So we will be computing 2 to this matrix A. And the first thing is to write A as a conjugate of some diagonal matrix to diagonalize it. So let's see if we can do it. First step in that is to compute the characteristic polynomial of A and see its root. And the characteristic polynomial is a determinant of A minus t times identity. T is a variable. In A, diagonal entries are zeros, so when I subtract t times identity from it, I will have this. And the determinant is what I'm after. Here, probably the formula is the easiest one. I will use the formula. Taking the product of diagonal entries, I will have negative t cubed. 2 more products with plus sign will be these 3 ones, which will give me 1 copy, and then this product will give me another copy of 1, so total plus 2. And then with minus sign, I have this product, which is itself negative t. Then these 3 things will give me another copy of negative t, and finally these 3 matrix entries multiplied give me 3rd copy of negative t. Each of these negative t's comes with a negative sign, so I have positive 3t in the determinant expansion. So that is the complete answer. I have all my 6 terms written. Now I have to find the roots of this polynomial. I have to factorize it. And believing in goodness, I will just look at easy roots first, like integers, maybe small integers. The free coefficient is 2, so if my roots are integers, they will have to be divisors of 2. If all the roots are integers, and then 1 is probably the easiest divisor, or maybe negative 1. If I substitute 1, I will have negative 1, but then too much in a positive, like 5. So if I substitute negative 1, I will have positive 1 here, I will have positive 2, making 3 here, and then negative 3 will cancel it out, so I'll have 0. The conclusion is negative 1 is a root, and so I can factorize my polynomial as t plus 1 and then something. So what is this something? Definitely negative t squared is its leading term. Definitely positive 2 is its free term. And then the only question is what is the linear term? And then matching things up in the product, in the linear term, when I open up the product, I will have t times 2, and then whatever this coefficient t is times 1. So that unknown plus 2 should be matching 3, which makes this unknown just 1. And we can check that the square term doesn't appear, because here we'll have negative t squared and then we'll have positive t squared, which will cancel each other. That is a good start. I already have one of my roots. Then 2 other roots are in this polynomial, and using the quadratic formula, which I will not be writing down because it is too boring, I will have another copy of minus 1 as a root. So I will have this root with multiplicity 2, and then I will have the root which is positive 2, and then overall sign of this factorization will be negative, because the leading coefficient is negative 1. So the eigenvalues, the spectrum of my matrix has 2 numbers, negative 1 and 2. But negative 1 is a multiple root. And finding eigenvalues, I will start with it. So first eigenvalue negative 1. To find eigenvalues, I have to basically plug it instead of t, look at the matrix as a matrix of linear systems, solve the system, write independent solutions. So the system will have this matrix, all one matrix, and it's easy to solve the system. It's just one equation effectively, so we can use Gauss elimination formally to get rid of all but the first row. And the first row is just saying that our coordinates x, y, and z, the coordinates of our vectors, solution vectors, sum to 0, or treating y and z as free variables, we can write x as their function. And then a generic solution will have these in place of x, and then y and z are whatever they are, because they are unconstrained, they are free. And then, sorry, that is y and that is z. And then grouping for y and z components of the generic solution, we will have following two basic vectors: -1, 1, 0, along y coordinate, -1, 0, 1 along z coordinate. So these are the two basic vectors which generate the solution space of the system. These are the two basic eigenvectors. We need to have linearly dependent basic eigenvectors, a basis of eigenvectors, to construct a transition matrix. So what we are after here is really writing A as G, D, G inverse, and the G will have to be built out of this eigenvector, so it has to be invertible. The eigenvectors have to be linearly independent. We have first two. Now we have to find the last one. That will be the eigenvector for eigenvalue 2. This time we have to substitute 2 into the matrix here. So -2, 1, 1, 1, -2, 1, 1, 1, -2 is the matrix for the second linear system. Again, it has to have non-zero solutions. That is a checking point that eigenvalues were found correctly. And to solve, let's swap the first and the last row, creating a nice pivot in the first pivotal position. And then start eliminating row 2 minus row 1, row 3 plus 2 copies of row 1. So we'll have 0, and then we'll have -3, and then we'll have 1 without -2, so it is +3. So here we'll have 0 made again through this row addition, and then we'll have 1 plus 2 copies of 1, +3, 1 plus 2 copies of -2, so 1 minus 4, -3. These two are proportional, can be eliminated, and at the same time we will scale, say, this one by 1/3 and make it the second, circumventing several steps, rolling them into one. And that is a row echelon form and one step away from reduced. To reduce, we have to just subtract from the first our second row, and then we will have perfect shape of our pivots. And in the process, subtracting -1 from -2, we will have -1 left. So that is a reduced row echelon form of the original system, and that harbors a solution which really says now that the only free variable we have is the last one, and then all other coordinates are just the same, because the first equation says that x is equal to z, and y is also equal to z. So that is one parameter family of solutions with the basic vector being vector of all ones. And that is now our last column of the transition matrix G. What is D? To make it all aligned with the arrangement of eigenvectors. The first two are with eigenvalue -1, so that is the first two diagonal entries in D. The last is with eigenvalue 2. And now we have to find G inverse, so we have to invert this matrix G. For that, we will use the formula which as intermediate steps has the cofactor matrix and then scaled by the determinant. So first, what is the determinant of our G? If we again use the formula, this is 0, this is 0, so this is 1 with positive sign. Then with negative signs, this product is 0, this product is -1, but with negative sign in the determinant is positive, and so is this product. So all in all, we have 3 copies of 1, the determinant is 3. The cofactor matrix, so first I'll just compute the matrix of determinants of this minus, so the matrix of minus. And then I will change the signs to make it them cofactors. So first, starting with this entry, that is the answer sitting in the cofactor matrix in the first position. I have to take the determinant of this corner, which is manifestly -1, and so that's what I write here. And then the minor for this entry is the determinant of the matrix 2 by 2 with 1, 0, 1, 1 as columns. The determinant is 1. For that, the determinant is of the identity matrix also 1. So this entry, taking its column and its row out, will have -1, 1, 1, 1 as a matrix row-wise, and its determinant is -2. Looking at this, we have -1, 0, and 1, 1. The determinant is -1. And this minor for this element is -1 again. Then this is coming with a minor negative of determinant -1. This will have the matrix complemented matrix -1, 1, 1, 1. The determinant is again -2. Finally, this is +1. So that was just the minus. We have just bare determinants of a truncated matrix. Now we have to adjust the signs. The signs on the diagonal are all plus as determinants. They're just already the answers for cofactors. Away from the diagonal, there will be minus, so we'll have to change the signs here, and then this again comes with its original sign. And below the diagonal, the same. So next to the main diagonal, we have to change signs. Here we don't. That is a quick mnemonic rule of how to adjust the signs to make to turn minus into cofactors. Then the answer for the inverse of G is 1 of the determinant, and then the cofactor matrix transposed. So 1 of the determinant is 1/3. Transposing this matrix will have -1, 2, -1, and then I'll just write the diagonal, which doesn't change. What was below will become above, and vice versa. And 1 here. So that is supposed to be the inverse of original G. Let's check it quickly. Say multiplying the first row by the first column, we will have negative is negative, negative is negative, positive is +1, totaling 3. 1 divided by 3 gives us 1, looking promising. That entry, sorry, this line by this column will supposed to give us 0, and -2, +1, and +1 will total to 0. So not continue with the check. That is the inverse of G. So we'll have this presentation, which we can now use to compute the desired the value of the function on our matrix. We will start with G, but I will just take this factor from the inverse in front of everything, so G will have these entries. Then comes not the D itself, but the matrix where our function 2 to the x applied to the diagonal entries. So 2 to the negative 1 will be 1/2. Again 1/2 in the next diagonal position, and the last entry will be 2 to the 2 is 4. Zeros everywhere else, 0. And then the inverse, but with 1/3 already accounted for. And finally, computing. Keeping maybe for simplifying computations, just taking all these denominators half, all these denominators 2, and taking them out of the computation again in front, making it 1/6, and then here should be 1, 1, and 8. That's what I will be keeping in mind when I will be multiplying this matrix with my diagonal. So when I compute the product entry in here, it is this line by that column, and again it is just 1, so that will be -1. This row by that column will be again -1. This by that will be +8 because 4 is doubled. This by that is +1. This by that is 0. This by that is +8. This by that is 0. +1 and 8 again. And that is the product of the two with 1/2 factored in front. And then I have the G inverse 3 times remaining. And now I have to multiply these two. So 1/6 is a prefactor for the whole answer. That by this, +1, so 2, and then 8. Total 10. This by that will be -2, +1, and 8. 8 without 1, it is 7. This by that, +1, -2, and 8 again. Already computed, it is 7. This by that, it is -1, 0, and 8. 7 again. This by that is 2 and 8, 10. This by that is -1 and 8, 7. This by that is -1 and 8, 7 again. This by that is again 7. And this by that is 2 plus 8, 10. And not surprisingly, the shape of like everything the same in the matrix apart from the diagonal stays put, because that shape is again robust through the preserved through algebraic operations which make up this function. So the shape is already a good indication that computations were done correctly, and really they are, and that is the answer for 2 to the power of that matrix. We'll stop here. See you later.